Well, let's take a few minutes to discuss Sn2 reactions. So these are substitution reactions, and there's really two options. We could have a reaction that happens all at once, which we would call a concerted reaction, or maybe a one-step reaction. And that might look like something like this. We'd have a chlorine, and we're going to learn that we call that a good leaving group. It is a stable anion when it's produced. Its conjugate acid is very strong, so we know that it's a very weak base. It's not very reactive. And if we use a nucleophile, that's really anything with a reactive lone pair of electrons. So this could also be considered to be a Lewis base. So anything that's a good Lewis base, like chloride or bromide, OH minus, SH minus, Cn minus. There's a lot of examples here. We're not going to list them all right now. But if this happens in one step where the nucleophile substitutes for the chlorine, we end up with this product, where now the chlorine has left, the nucleophile is attached to the carbon chain. The other option, so concerted is one option. The other option is a stepwise process, and that typically happens with tertiary alkyl halides or similar. Again, nucleophile, same as what we discussed a minute ago. The first step, though, is simply creating a carbocation by losing that leaving group. The second step is adding the nucleophile to the cation to ultimately substitute the chlorine for a nucleophile. But this is a two-step process. We're going to call the first one the one-step process, Sn2. We're going to call the stepwise process, Sn1. And our discussion in this video is going to focus on the Sn2 process. Well, let's look at the kinetics of this Sn2 process. So scientists have studied the rate of this reaction. As we learned in general chemistry, you can come up with the rate law if you systematically vary the concentration of the different pieces of the reaction. So let me redraw this up here so that we remember what we were talking about. So we are substituting the chlorine for a nucleophile. We have what's called the alkyl halide. We have the nucleophile as listed there. So we have two components to this reaction. So the rate is going to equal to the rate constant times the concentration of the alkyl halide times the concentration of the nucleophile. And I would prefer to use substrate instead of alkyl halide, because as we'll learn shortly, substitution reactions do not always take place using only alkyl halides. So if we talk about the compound that has the leaving group as the substrate, that makes this a little more general for us. So you can see there are two components, and by varying the concentration of those two components, scientists discovered that both the substrate concentration and the nucleophile concentration are responsible for the rate of this reaction. So for instance, if we were to double the substrate concentration, if we put in twice as much alkyl chloride in this case, we would have a rate that is doubled. If we were to instead double the amount of the nucleophile, put in twice as much nucleophile, all else being equal, we'd have a rate that is doubled. So this reaction is first order in substrate and first order in nucleophile, and so we call it a second order reaction overall. Because basically the exponent of each of these is 1, it adds up to 2, so we call it a second order reaction. If we had a third component that was in here, it would be called a third order reaction. And so we come up with the term Sn2, substitution, nucleophilic, bimolecular, meaning we have a second order reaction that the rate is dependent on both the concentration of the substrate and the concentration of the nucleophile. So let's look a little bit closer now at the mechanism of this Sn2 process. This is probably going to be one of the simpler mechanisms that we observe this semester. So here is an alkyl chloride, propyl chloride in this case. It's also going to be called the substrate, and we could use the nucleophile here. You could use the general nucleophile. I'm going to put in a specific one just because it's a little more interesting. I'm going to use Cn- as my nucleophile. And in this step, remember we learned that it is a concerted process. Everything happens at once. And so the nucleophilic attack, which is this arrow right here, happens on the carbon bearing the leaving group, and then the loss of leaving group happens at the same time, and we end up with our nucleophile now attached to the carbon chain and the leaving group floating along as a nice stable anion.